Now I want to conclude this video with a brief discussion of quantum computation on many qubits. So at the beginning of this module, we saw that a state of 2 qubits is a superposition over 2 to the 2, so 4 standard basis states. A state of 3 qubits is a superposition over 2 to the 3, so 8 standard basis states, and so on. So in general, an n qubit state is a superposition over 2 to the n standard basis states. Now, we can certainly keep track of how an n qubit state evolves under the action of quantum gates and measurements by hand. And indeed, we did this even in this video for very small examples. However, these calculations quickly become intractable as the number of qubits n grows. In fact, just for 400 qubits, there are 2 to the 400 amplitudes to keep track of. And the number 2 to the 400 is actually more than the atoms in the whole universe. So it is thoroughly intractable to even write down all of the amplitudes of a 400 qubit state. So how does a quantum computer, or a quantum system in fact, do it? Well, the catch is that the quantum computer does not actually calculate all of the 2 to the 400 amplitudes, but it merely evolves a state of 400 particles. You can think of a qubit as a particle. And it does so by inducing some physical transformation on these 400 particles. And you can think of a physical transformation as corresponding to some quantum gate. Now, the point is that we don't directly see all of these 2 to the n amplitudes as classical beings. These amplitudes are working under the hood, but all that we can access when we measure n qubits is n bits of information. Right? If we measure 3 qubits, we get 3 bits of information. And so really taking advantage of what the 2 to the n amplitudes are doing behind the scenes requires carefully orchestrating the constructive and destructive interference amongst them, so that amplitudes corresponding to the wrong answers to the problem we want to solve interfere destructively and they cancel each other out, and amplitudes corresponding to the right answers interfere constructively and they reinforce each other, so that when we measure at the end, what we obtain are bits corresponding to the correct answer. And this process is really at the essence of constructing algorithms for quantum computers.